Okay, so so this slide basically just covers how we can model the dynamics of an MAV. So basically, this is not regarding the control yet, not directly. So first of all, we can model the translational and the rotational dynamics. So this is just based on the Newton-Euler formulation, where we say that the time derivative of the position is just the rotation times the velocity of the body frame, and then rotate it into the inertial frame. So this is what this RIB stands for. And we can model the acceleration in the body frame by this gyroscopic term, which, as we say here, is usually relatively small, plus the acceleration along the body z-axis. So this is why x and y are both 0 here. So the lateral axes of a quadrotor or of a hexarotor are always 0 in their control allocation, because a standard quadrotor or hexarotor can only exert vertical accelerations because all the propellers are aligned in the same fashion, that they all create forces or accelerations vertically. And then as a third part to the acceleration, we also have the gravity, which acts in the world Z frame or Z axis. So we have to rotate that to the body frame. So this is where this term comes from. And then for the rotational dynamics, we get this equation for how the rotation, so attitude changes, which is a function of the angular velocity. So this hat in here stands for making the angular velocity to the to skew symmetric matrix. So this basically here is also like the time derivative of the matrix that gives us the rotation from the body to the inertial frame. And for the angular acceleration, we get again this gyroscopic term plus the angular accelerations around the x, y, and z axes. So this u2, 3, and 4, together with u1, are our virtual inputs that we define according to the geometry, which we see in another slide. So this is just for the modeling. This is not even the control yet. And then we use all, so for the modeling itself, for the control itself, again, I just talked already about the virtual inputs. So what we do is we have this formulation that connects the virtual inputs u1, 2, 3, and 4 to the rotor speeds via this geometric allocation matrix. And this geometric allocation matrix depends on the length of the arms, for example, and also the thrust coefficient CF. And this is something that you can set up by looking at how the vertical thrust and the accelerations around X, Y, and Z, so the torque accelerations, depend on the rotor speeds. Okay, we got another question, what the omega hat meant. Omega hat, okay, wait, maybe I can, I don't know if this is written anywhere else, but basically we use omega, which is the angular velocity. So it's just like omega x, y, and z. And we use this hat operator to make the vector into a skew symmetric matrix. So you can probably look this up online, what this means. I think it's not written anywhere here. Like basically it makes a vector into a skew symmetric matrix. And then again, coming back to the controller now, we always have this hierarchical or cascaded control, basically, where we say we first, in a slow loop, basically want to control the position. And as a result of the position controller, we get a desired rotation matrix. So basically a desired attitude that we want to track with the attitude controller. And the reason for this is basically that we cannot directly control the position without changing the attitude of an MAV. So basically imagine if you fly horizontally and if you want to change the position to go from here to there, then you cannot just directly, without changing the attitude, traverse horizontally, but instead you have to pitch or roll, move over and roll back to stay at this attitude, at this position. And the reason for this is that you can, again, only exert vertical accelerations, like vertical in the body frame. So if you want to accelerate horizontally, you need to tilt, accelerate over, and then tilt back. And this is why the position controller always gives us a desired attitude that we need to achieve such that we can change the position. This is why we separate position and attitude controller. And this is also why we have this one arrow for U1, so for the vertical acceleration that goes out of the position controller into the allocation. So this is just the Z acceleration. And then the attitude controller only gives us angular accelerations that are required to achieve some attitude. And so looking at this first part, I'm going to go into the questions again. So the question is, what do we mean by attitude? Attitude is the orientation of the platform. So roll, pitch, and yaw, basically. Then for the first part, the position controller, again, we take as an input the desired position, the desired velocity, maybe also the desired linear acceleration. And out of that, we get a reference attitude, orientation that we want to track. And the question is, how do we get from, let's say we are at current position P, we want to get to a position P desired. So how do we get the attitude that brings us there and also the acceleration that brings us there? So what we do is we basically just use a PD controller that's based on the position error and the linear velocity error. And then we create this desired attitude by creating the three axes of this desired attitude individually. So first of all, the desired z-axis of the desired attitude just follows from this PD term, plus also the gravity compensation. Then once we have the z-axis of this desired attitude, we can create a temporary x-axis. And you have to think about this temporary x-axis as giving us the heading that we want when we get to another point. So imagine again that we start here and we want to go over here. Then it doesn't matter how we're headed. Like we can go sideways or we can rotate and we go forwards. So we can choose the heading, how we want to go from one point to another, just however we want. And this is defined by this psi or this psi desired, which it gives us the heading. And by that, we create this temporary x-axis. And so then this previously computed z-axis together with the temporary x-axis gives us a y-axis by the cross product, because we know that in the attitude reference frame, all the axes have to be perpendicular. So we just use the cross product. And then once we have the z and the y-axis, we can finally create the x-axis by, again, the cross product. So this seems quite complicated, but we only do this to have a rectangular or orthogonal system for x, y, and z. Yeah, so basically by the position controller, we create the reference attitude with this like built together by x, y, and z, which is then fed to the attitude controller. And the attitude controller, based on the error, gives us then the angular accelerations u2, 3, and 4, which is, again, just based on a PD controller. And the PD controller is based on the attitude error, ER, and the angular velocity error, E omega. And this again also comes back to the previous question before about this hat operator. So this here is basically inverse. So we compute the attitude error, like by this term down here. But this term itself here is still a matrix. So you see, we just multiply rotation matrices with each other and in the end, we have this 3 by 3 matrix. And we use this V operator to only take the elements in some certain positions of this 3 by 3 matrix to get a vector in the end. So this is the exact inverse of the hat operator that we saw before. Then there was another question, how is the position expressed? The position is usually expressed in a global inertial frame. Yes, that's correct. And regarding the scale, we usually just use meters, for example. Regarding advantages and challenges using MPC, so this is not so easy to answer directly. So there's different methods on how we can use MPC, so model predictive control for MAVs. So we can use it on a high level to only create paths that we want to track. And then it's okay to only update with a low rate, so only with 10 Hertz or 5 Hertz or something like that. And in that case, it works quite well. But MPC is more difficult to use if you really want to use it as a controller, because typically MAVs require really high control rates, like 100 or better, even 200 or 250 Hertz. And running MPC at 250 Hertz is usually not so easy, and you would need a really strong computer. So yeah, it is very advantageous if you can include all the dynamics and constraints, but you have to think about at what rate you want to use the MPC. Regarding the interpretation for this attitude error, ER, I think the easiest interpretation is the angular difference around the X, Y, and Z axis from the current attitude to the desired attitude. So it is kind of similar to the difference of the yaw, pitch, and roll angles if you are just in zero roll pitch, hover. But it works for all other attitudes as well. So you don't have to be in zero roll pitch, but you can also be in any other attitude, and it's always going to give you the smallest approximation of the errors around the X, Y, and Z axes. Then again, coming back to MPC, computed on an external server. Yes, so you could as well use a really strong computer that's not on the platform itself, that handles all the very complex computations. But then again, you might have some delays, which you also don't want to have. So just in the communication from this external server to the platform itself. And if we want to use a controller that runs at 200 Hertz, then delays of like 5 milliseconds are already too long. So this might work in terms of computational power, but in the end, you again have some delays that you don't want to have.
If there are no immediate other control questions, there was a question about the Kalman-based versus graph-based state estimation. Quickly share my screen. So one of the, or how can we like define the difference between the two? I'll quickly explain again how they work, and then I'll discuss a bit the relative pros and cons and why are they different, or why both of them exist. So here I have this slide from the case study about how visual inertial odometry with a filter works. So basically, a Kalman filter, you have two major parts of a Kalman filter. One is to predict your future state according to some model or some data, and then to update the belief state that you get by prediction using a measurement update. And in visual inertial odometry, this works in the way that on the left you see the current state, so to speak, in 2D, where xt is the position, pt is the covariance. So we have a covariance here that tells us how certain we are about the current state. And then we forward predict that using the IMU data. And because we know that the IMU data is very noisy and has a lot of biases, this increases the covariance. So we propelled our state forward, but we're also less certain about our current state because of the noisiness of the IMU. This is then followed by an update step using the things we see on the camera, which then corrects the state and shrinks the covariance again, because we know the features on the camera have a better quality, a lower covariance. So, and this is an iterative filter. We only need to keep our current state and the current covariance and just go through this scheme time and time and time again. In theory, as you might know, a Kalman filter, like a standard Kalman filter with a linear model, is guaranteed to give you the optimal solution for Gaussian noises and linear process models. So here the process model would be the prediction step. And of course, also linear observation models, which would be how we model the patches, how they influence the position. That's in theory. In practice, most noises are not so Gaussian. I mean, the one on the IMU, you could argue that this behaves similar to a Gaussian because it's kind of a natural noise, whereas the noise on the patches is for sure not Gaussian. If you mismatch a patch somewhere, it could be anywhere on the screen, so you could even argue it's sort of a uniform noise. Also, the observations and prediction models are, of course, not linear here. So these are all approximations we make. They work really nice in practice, but there is no guaranteed theoretical boundary that this gives us an optimal solution. And what the Kalman filter doesn't do, it doesn't correct its previous states. It only knows the current state. In contrast, the optimization or graph-based systems, maybe we'll start with this slide. They build up a time history of all your measurements. Here, the green dots are sort of what we see, and the red ones, what we feel on the IMU. And those measurements, they connect states in time with landmarks. So we see a specific landmarks at a specific position, we believe, and the states themselves are connected by IMU measurements. Now, all this graph magic is just here to give us a way to formalize an optimization problem. So in graph-based optimization or in optimization-based state estimation, we take the last X steps, let's say last 10 or last 100 steps, depending on how much CPU time you can afford and how complex the problem is, and derive all the error terms between where we believe that state was and what we saw and felt during these states. So as an example, if we go from one state to the next, the IMU might tell us, oh, we rotated by 90 degrees. The landmarks tell us, oh, we rotated by 89 degrees. So what do? Probably the solver comes up with something in between or trusts the landmarks more because we know these are more exact. But the important thing is you look at a succession of states also in history and solve for the most likely, or in this term, the trajectory that gives you the lowest errors with all these connections of key point measurements. Of course, this takes a lot more CPU because you have to look at many landmarks and many IMU measurements and many states simultaneously. And this can also fail. It's seldom that you can prove that this error terms or this optimization problem is convex, meaning the solver might find many local minima that give you a little bit different results. And sometimes it gives you completely useless results, depending on how the problem is built up. But on average, it has less error because it incorporates past measurements. In a linear Gaussian world, both of these should converge to the equal solution, but because we always have these approximations everywhere, it depends a bit in what use case, which one works better. So if you need something that updates really, really fast, you're better off with a filter-based solution. If you need something that can optimize, let's say, a trajectory over the last 5 minutes and you want everything to be as consistent as possible, you would go with a graph-based one. I hope this somewhat answers your question. Yes, I think there is no more perception questions, so I'll hand it back to Max.
Yeah, so a lot of times, I guess the question of how you can find the allocation matrix comes up. So I will try to draw online. I don't have any iPad or something, unfortunately, to show this better, but I can try to do this online. Let me share my screen again. All right, so usually when you have a quadrature, we often use the NED frame, which is called north, east, down. So this is what I drew here. We have a quadrature. We have the x-axis pointing forward, the y-axis to the side, so east to the right side, and the z-axis down. So this is where this NED frame convention comes from. And then the question is how we can find the allocation matrix. And again, the definition of the allocation matrix is basically how we relate the virtual inputs to the rotor speeds. So, sorry. So how do we get the vector of the u's as a function of the allocation matrix A and the squared rotor speeds omega, or omega squared? I'm sorry for not being able to draw so well here. But then the idea is that we always define these virtual inputs to be u. One is the vertical acceleration in the body z frame. So usually we now assume that all the forces created by all the rotors point upwards. So these are all the individual forces which depend directly on the squared rotor speeds. So then we have u1 pointing upwards. We have the u2 is the angular acceleration around the x-axis. So this would be this one here. This is u2. u3 is the angular acceleration around y. And u4 is the angular acceleration around z. And because the question just came up, the thrust is always perpendicular to the rotor. Yes, so the thrust produced by each rotor is always perpendicular to its blades, basically. And then we want to find this linear relationship between u1, 3, and 4, u1, 2, 3, and 4, and the rotor speed. So we also have to somehow find numbering for all the rotor speeds. So we could say, for example, that this one is omega 1, this is omega 2, omega 3, omega 3, and omega 4. And then you basically just have to look at the geometry. Let's say that the length from the origin, so from the center to the end to each arm would be, let's say this is r. Then how can we find u1 as a function of all the rotor speeds? And u1 is the vertical acceleration. So we just see, okay, the vertical acceleration is not even a function of the distance, but it's only the sum of all the rotor speeds squared. So basically, this is just CF, so the thrust coefficient times omega squared. This is a force produced by a vector, and we sum this up over all the 4 rotors that we have here. So this would basically already be the expression for omega for U1. Then for U2, and I'm only going to go through that one now because the rest is then basically done in the same way. So for U1, for example, we want to find out how the angular acceleration around the x-axis is a function of the rotor speeds. And now we see that U2, so the angular acceleration around x, does only depend on omega 2 and omega 4, because only these two contribute to the moment or to the torque around the x-axis. So basically this is then if we look at this one here first, this creates a positive torque around the x-axis. So this would be R times omega 2 CF omega 2 squared plus R, oh no, I'm sorry, this is actually minus because this omega 4 creates a negative torque around the x-axis, so this would be then minus R omega 4 squared CF. And then you can do the same around the y-axis with omega 1 and the omega 3. And then actually around the z-axis, there's something more specific, so I'm also going to write this here. So U4, this is the torque around the z-axis, is not created by the direct arm length times the force, but instead it's only created by the drag torque that all the rotors create. And here we have to know that the rotors rotate in different directions. So usually this is alternating it. For example, this rotor omega 2 rotates, in that case, counterclockwise. Omega 3 rotates clockwise. Omega 4 again rotates counterclockwise, and omega 1 clockwise. Sorry, other way around. No. Omega 1 again rotates clockwise. And then omega 4 is the sum of now CD, so the drag torque, times omega squared, times the rotation direction. So this would be then usually -1 to the power of I. So depending on what rotor we look at, we have to do plus or minus the rotation speed squared times the drag torque to get the total torque around the z-axis. So I hope this kind of gives you an idea on how you can compute the allocation matrix. And then, of course, you can make this more complicated by using 6 instead of 4 rotors, or maybe even have them aligned, like not perfectly aligned with the XY plane, but slightly tilted. But basically, the principle is always the same. You always just look for the force that's created by each rotor, the distance to the origin, and the drag torques. And by that, you can set up this allocation matrix. Regarding question why we call this virtual, I'm not exactly sure where the exact expression virtual comes from, but I assume it's not really existent, right? We only use it as a mathematical step to get our angular velocities, but it's not an actual actuator input. Like it's not really existent physically. So this is why we call it virtual. So if we want to move along the y-axis translationally, then yeah, basically, as you write already, you have two options. Usually, the faster way would be to only rotate along x, and then by that create this acceleration around along the y-axis. But of course, now if you want to do more fancy high-level motion planning, then you can also rotate the yaw first. But usually, we take the most direct way. So that means if we want to move along y, we just rotate around x, go along y, and rotate back. So the question is that if that would create a drag torque around z if we tilt around x, but usually this is not the case. So this is why this is decoupled nicely. So U1, 2, 3, and 4 are decoupled in the sense that we can create only a rotation around the x-axis without creating a yaw torque at the same time. So the question has been coming up what the gyroscopic term, this omega cross j omega, stands for on slide 24. But honestly, on slide 24 in the case study, I don't see it. But basically, the omega cross j omega arises mathematically and comes from the fact that the frame that we're controlling in is rotating, or it might be rotating. So basically, if you take the angular dynamics and or the angular rotation, and if you take the time derivative, then this term just follows from the time derivative and needs to be compensated for. But what it physically means, how we can understand it, I cannot really explain. So the question is, what makes the trajectory tracking controller more stable than the attitude controller? And I think you're referring to the geometric controller. So the one that we looked at in the case study. So because in the case study we use a very specific attitude error formulation. So as opposed to the lecture. So in the lecture we just used, in the previous lecture from 2 weeks ago or 1 week ago, we only used the Euler angles, yaw, pitch, and roll, and took their differences between the reference and the actual Euler angles to compute with a PD controller the angular accelerations. And this works for small angles, which is nice. I mean, this only works for small angles, like up to, I'm not sure, 10, 20 degrees. But if we have larger attitude errors, then the Euler angle approximation does not work anymore. So then we just have too large angle errors. And the nice thing about the geometric controller, or the attitude error computation with the geometric controller, is that it works in regions up to 180 degrees. So it will always bring the attitude error back to 0 for attitude errors that are up to 80 degrees, 180 degrees large. So it's just more general than the Euler angle formulation.
Max, I think you're muted. Sorry.
I'm sorry. I'm not so good with technology, apparently. So again, yes, so the geometric controller is better than the Euler angle controller because we use the more exact attitude error, which is written here. And also coming back to the allocation, it's correct. So from the attitude error, we compute the angular accelerations, u2, 3, and 4. And then we feed all this together with the linear acceleration, u1. And then we get the omega, so the angular velocities, by inverting the allocation matrix A. So basically omega 1, 2, or omega 1, 2, 3, 4, depending on how many rotors we have, is A inverse times the virtual control inputs.
There was a question about the ability to fly through a small tunnel. It's actually quite an interesting question. I mean, whenever you get close to surfaces, or if you're not in free air anymore, many of the assumptions we have in formulating controllers may not hold completely anymore. One very common effect is ground effect. So when you get close to the ground, the drone or also a fixed wing plane has the same problem, hovers on a sort of air cushion and needs less energy to keep itself up. Vice versa, if you fly very close to a ceiling, at some point you create some sort of suction to the ceiling, which makes it more efficient to stay on that ceiling. There's even a paper from, I think it was a Japanese group that exploited this to keep attached to the ceiling. So yes, it is kind of a problem. Whenever you get out of free air into a different airflow regime, it's quite hard to predict what will happen. Oftentimes the controller is stable enough so that it just, without knowing a model for all of this, it just kind of still performs okay-ish. It just feels, oh, my attitude is changing in this direction, so I put more thrust on that propeller. And it might be because that propeller is at the moment aerodynamically more or less efficient. There are people that are modeling things like that. Also on bigger MAVs with tilt rotors, we have interference between the rotors as well. So Weishuan, who is doing the exercise tomorrow, is modeling a lot of that. There are also people modeling effects close to the walls, but because it's computation fluid dynamics and it's very turbulent, it's really hard to model. So it's often you try to have a controller as stable as possible, and then you basically give it a try. And if it doesn't work, you figure out how you can make it work. There are some regimes, for example, if you want to fly very close to a corner, it might be really, really hard to achieve stable flight because the airflow is all over the place. I hope this answers your question somewhat. It's really depending on the geometry, really depending on the controller. So it's hard to give like a generic answer. Usually, as long as you have enough distances to the wall, let's say at least one size of a rotor, you can kind of make it work. So I think we have about time for a very short last question. Otherwise, feel free to ask on Piazza. There is one good question actually coming. The sensor getting the air disturbance. Yes, there are experiments. Some people use pressure sensors on little tubes to sense the pressure difference at different locations. There is also a paper from a former student of ours, Andrea Tagliabue, where they tried sort of whiskers that give you information about the airflow. There are also optical methods where you try to, like with these Schlieren effects, try to see airflow, how it evolves. But all of this is really, really in its like infant steps, and it's also really hard from one sensor to make assumptions about the three-dimensional airflow. Cool. So I guess that's it. As I said, feel free to ask on Piazza. Also, Weishuan, that is doing the exercise tomorrow, knows a lot about MAVs. So if you have further questions, you can also ask him. If you're interested in a semester thesis, master thesis, check out our website and our YouTube channel to get an idea what projects you're working on, and feel free to shoot us an email if you're interested in something. Cool.
Right. Thank you, guys. Bye.
Bye, everyone.